One will be a CLI application. That's the space where GraalVM is quite popular because it can give you fast startup, small packaging, low memory footprint. Then we will hopefully build a full stack web application using GraalVM. Then we will build an LLM inference engine, and I mean engine, so an actual kind of DIY LLM that you can build yourself and run on your local machine instead of calling something like OpenAI, Claude, etc. Then we will talk about performance optimizations, because I know that as Java developers, we want to have our high peak throughput. We cannot do without it. Then we will talk about how you can make your application even more secure. GraalVM adds a layer of security out of the box, but then we will talk about how we can make our applications even more secure. And then if we have time, which I don't think we will have because I love chit-chatting, but if we have time, there will be a bonus application using Python. And then I will briefly mention what are our future plans and what will be the next big things for GraalVM. Let's go. So I was kind of hoping that I don't need to do this intro anymore, but I've been at a few conferences recently where people asked me, those like basic questions: what is GraalVM, where should they use it? So maybe we can do a quick 1-minute intro to GraalVM. So GraalVM is a JDK, just like any other JDK of your choice. And the thing that I need to remember is that we add things to the JDK. We don't remove anything from the JDK. So it's like a JDK on steroids in a way. And one thing that we have added is a GraalVM JIT compiler. This is something that has been a result of our 10 years of R&D at Oracle Labs. So a brand new, highly optimizing compiler, and you can think of it as an alternative to C2, the top-tier, highly optimizing compiler in OpenJDK. So if you just swap to GraalVM as a Java runtime, you can get somewhere 10–15% performance improvement just by using a better JIT compiler. Now, something that we will focus more in this session today will be native image, and this is ahead of time capability of GraalVM, where we can compile the application ahead of time into a native executable that will start very fast and use fewer resources. And lastly, we love Java and we love JVM languages, but there are more languages that we can run on GraalVM. So our team has implemented many of those languages that you see here on the screen. So you can use GraalVM to run JavaScript, you can use it to run Python, and you can even embed JavaScript or Python in a Java application. What's funny, if you wanted to be a language implementer yourself, if you wanted to have your own language implementation, this is something you can do with GraalVM because we give you a nice implementation framework and API. So if you always wanted to implement something, there is a fun community project where a student in his free time in one semester implemented PHP on GraalVM. So I'm not necessarily encouraging you to implement PHP, but if you always wanted to have your own language implementation, GraalVM and Truffle could be the way to go. Now, why native image? And if you have any questions about the JIT compiler or Truffle, so other languages, I will be happy to answer during the break. But in this session, we will focus mostly on native image and this ahead of time compilation. So what is it and why native image? Very quickly, because I have a lot of demos that I want to show. So native image is a part of GraalVM that compiles your application ahead of time. So as you are building your application, in the end, instead of a jar, you have a native executable. Kind of if you would have written it in something like C or C++, but you can still write it in Java, and in the end, you have a tiny, small, very fast native executable. So you still have your developer experience from Java, but in the end, what you actually run is a native program. And this happens ahead of time at the build time, so it needs to happen under closed world assumption, meaning that unlike the JVM, out of the box, you cannot load new classes because everything there is to know about your application needs to be known at build time. And if you want to use those more dynamic Java features, such as reflection, serialization, proxies, etc., those need to be configured at build time. So this is one important thing to remember about native image. And the idea there is to move all of that work that the JVM normally does at runtime, so loading classes, interpreting, compiling, profiling, etc. Move all of that from runtime to build time because we think that most applications are started way more often than they are built, so it kind of makes sense to build them once, and then every time you need to deploy or scale or start new instances, you can do so faster because all of that overhead has happened at build time. And if you were in Holly's keynote this morning, she was making a good point about efficiency of applications. So if you want to have applications that are greener, that are using less CPU, less memory, etc., native image is what it gives you such a possibility by turning your Java applications into native executables. So native image gives you this fast startup and low resources usage because we did all that overhead work that the JVM normally does at runtime. We did that at build time. It also gives you what some people call predictable high performance or instant performance because your application does not need to warm up. So if you were to imagine the throughput of your application as a line, as a graph, it will be very stable from the very first milliseconds because there is no this kind of warming up curve and overhead. It also gives you additional security. We will talk about that down the line. And compact packaging. So if you want to have smaller container images, if you want to have smaller deployments, you don't need to include the JVM. That's the whole point of native image. You just have that native file that includes everything that you need and only the things that you don't need, and then you remove those other parts that you don't need. Okay, and we also have a lot of framework support. So whatever is the Java framework that you like, Micronaut, Spring, Quarkus, Halidon, all of them work like a charm with GraalVM. Now, that was a lot of talking about the benefits, so let's see how those benefits transfer into each of those applications that we are going to build. So one type of applications where we see a lot of love for GraalVM is CLI applications, because normally for CLI applications, you want them to start fast. If possible, you want them to be smaller. And also, they should use less resources because they're not doing that much work. I'm wondering how many of you in the room are building CLI applications? Okay, quite a few, maybe like 20, 25% people. So there are many options how you can build such applications. I want to start with a notable mention of Pico CLI. That's a very nice framework that helps you build CLI apps, and it works very easily with GraalVM. So that's something you can try, but I personally like Spring a lot, so I decided to go with Spring. So let me show you what I have built. Okay, let's see. I hope this is visible enough. How is it in the back? All good? Okay, cool. So let's start with our CLI application, and I have already compiled it here. So my whole application, it's called Native Spring Shell because it uses Native Spring Shell. So Spring offers this module for building shell applications, and my whole application is 40 megabytes, which I think is pretty good. And if you look inside the app, it's fairly trivial. So it has our main class for this shell application coming from Spring. And then I have one more class that I have created that is implementing ls, so the Linux utility for listing files and directories, but it's doing so hopefully in a more kind of cute format. So that's all our application does. It's a kind of more cute, more user-friendly alternative to ls. So let's run it. Target native Spring Shell. Oh, and I want to share a fun fact with you that I have learned when I was working on this. So do you see this banner here? If you ever wondered how you can add a custom banner to your application, that depends on the framework. But if you happen to be a Spring user, apparently it's very easy. You just drop this banner txt under resources, and this you can generate online with all those like SKR generators, and you can have your own cute banner for your Spring applications. So that's a side note, but I think this is pretty cute. So our application has started, and it's pretty quick, as you can tell. Just let me go this up so we can have more space. So our application has started, and then there are a bunch of utilities that Spring does for us out of the box. We don't need to implement them. So if we do help, we see all those built-in commands such as help, history, quit, etc., versioning, and then there is the ls method that we have implemented. So if we call that method, we get, hopefully, I think we can agree, a more cute version of ls, where we have emojis and colors and stuff. And then we can also go and retrieve words in our target directory, and then we can call history, and it all works. So this application doesn't do much, but clearly we can extend it, and hopefully it gets across a point of how easy it is to build applications with GraalVM, and also how fast and small they are, because this one started in just 65 milliseconds, I believe. So that's it, and it also gives us things like quit and exit, and all those commands just come out of the box, and I believe Pico CLI offers a very similar kind of built-in set of commands. So whatever you choose to go with, Pico CLI, whatever other framework support offers, or Spring Shell, it's very easy to build such CLI apps with GraalVM. So that was a CLI application. Now let's talk about building something a bit more meaningful, maybe something that you happen to be building at work, more maybe enterprisey or more also user-friendly. So if you were to build a full stack application, maybe what you want from it, if I had to guess, would be also to start fast, because it's always nice to start fast. Your users don't need to wait for the application to come up, and also you don't need to spend that many resources if you're maybe in the cloud. Compact packaging would also be nice if you want to deploy such application fast, but also for those kind of full stack web application, now performance becomes a bit more important, because again, if this is something you have deployed somewhere in production, you want it to be fast, right? And there are multiple ways, again, to build such applications. I want to give notable mentions to Vaadin and JHipster. And there are a few sample projects here that you can give a try if you want to replicate such an app and see how it behaves with GraalVM. So JHipster is also pretty cool, but I will go here with Vaadin, because the way this project came to be is in the past I built an application to showcase Spring AI. So the one, if you want to try out, is here on the top. But there, the front end was just plain HTML and CSS that I wrote, and I'm clearly not a front-end developer. So Marcus here from the Vaadin team looked at it, and he was slightly shocked, and he decided to create a slightly, not slightly, much better UI with Vaadin. So let's see how it works, and it's also obviously compiled with GraalVM. So let's see that in action. For that, let's go to this intriguing application called Travel Tips. And this will be our travel tips application that, as you can guess, gives us recommendation for places to travel. In a nutshell, it's a Vaadin application that uses Spring under the hood. Here we have our nice front end, and then our Java sources and configuration files and everything are under Java. So let's run it and let's see what it does. Now, this one is a bit bigger, I must say, than the application that we have seen before. Where is it? It's 183 megabytes, but this is not built with optimizations for size. If you're curious, there is additional flag -OS that can help you produce smaller images if the image size or container size is your kind of priority and concern. I did not do anything at all. This is just plain out-of-the-box application. And let's see how it behaves. So target travel tips. But it starts pretty fast, I would say, in under 100 milliseconds, which, again, for a full-stack web application using frameworks, libraries, etc., I would say is quite decent. So when we go here to our endpoint, we see that it's indeed what seems to be a travel form that can give us recommendations for places where we want to travel. And I think we can agree that it looks better and looks more modern than things that at least I could have written manually. So let's see how it acts. And under the hood, it uses Vaadin, and then it uses Spring AI to call OpenAI and generate travel recommendations based on our priorities. So let's say we want to travel to Coimbra, and we want to specify some kind of interest, things that we want to do in case, we want to get personalized recommendations for our travel priorities. So let's say our interests are books and gelato. And then we need to set the mood that we are in, and this will now go and make a call to the OpenAI. And as I was talking, it's actually already back, and it's giving us recommendations to visit some libraries. There are some tips for gelaterias, and it says to take a walking tour, and it all sounds pretty good. But also, if any of you are local, tell me afterwards if those racks are good for books and gelato. I would appreciate your recommendations. But overall, I think this is a nice example of a full stack application that uses GraalVM under the hood, and I think you can agree that it's fairly compact for such a full-blown web application, and it also starts very fast, and all of that comes from GraalVM. Okay, so this was our full stack application. But there are more fun things that we can build with GraalVM. So in this case, we were calling OpenAI to get that LLM-generated recommendation for our travel. But maybe we work in some kind of resources-constrained environments. We don't want to call OpenAI. Maybe it's prohibited at where we work. Or maybe just as a fun project, we want to implement such an LLM locally and kind of make it DIY. So how is it possible, and how does GraalVM help with that? So this is getting into a bit more kind of fun area, but I think it's a nice representation of what modern Java can offer for us and also how GraalVM can optimize it. And what we will talk about here is a project done by my colleague. Here on the bottom, you can find a link to the sources on GitHub. And what this is a complete LLM engine that you can run locally. So what I mean by complete engine, and let's maybe switch and run it ourselves. So what this is, if my code will collaborate with me, okay. So this will take a while to explain, but in a nutshell, this project that you can also find on GitHub is called llama3.java, and this is a complete LLM inference engine. So what do I mean by LLM inference engine? Along with a model file, and the model file is the one with the format of gguf over there. Along with a model file, this one Java source file, so the whole project is just one Java source file. This makes up a complete LLM inference engine. By inference, I mean that this does not do a training of the model, so this is not a complete LLM in the way that you can train it, but as long as you have a model coming from Llama or Mistral or whatever, this Java files handles the rest of the logic. So interacting with the user, tokenizing the input, tokenizing the output, choosing the next token in the sequence, etc. All of that business inference logic is encapsulated in this Java source file. And one might argue that this is a fairly long file, but I would say that I have seen in my life longer Java source files. And again, this is your complete engine logic. So along with this model file, it does everything that you need to do to have this LLM logic running locally. So the way to set this up, if you wanted to recreate this yourself, would be to clone this from GitHub to get a model from places like Hugging Face, and then you can do this whole LLM running locally, kind of like Llama in a way, but you don't even need Llama and you don't even need Docker. The whole logic is defined in this Java file. So why do I think that this is a nice showcase of Java? Because sometimes when you talk to people about LLMs and ML and in which languages to do it, they will tell you that you need to use necessarily Python because Python has all the best libraries, or that you necessarily need to use native extensions from things like C, because if you want to make something fast, you need to write it in C to get that near to the metal performance. But no, we did it in Java, and we used 3 key things to implement this. So one is the FFM API from Java to work efficiently with this big model file. The second one is vector API to make those computations faster, because it's a lot of vector multiplication, and vector API is what makes it faster. And the last part is GraalVM, because then we took this Java file and we compiled it to native image. And moreover, we included some of the model data as we were building the native executable. So by including those GraalVM's optimizations from the compiler, but also from native image, this file is very fast. This was a lot of explanation trying to fit into 5 minutes, but let me maybe show you that application in action. So let me actually show you how it looks compiled. So this Llama 3 is 66 megabytes, and this is my complete engine that, along with the model, makes up the whole kind of LLM execution environment. And one more point, I'm running this on my local machine, so the previous demos were running on a cloud instance, but this one is running just on this fairly old MacBook, just on CPUs, not even using GPUs, and as we will see hopefully in a second, it is pretty fast. So let me run Llama 3, and let me pass the model, and the one that we have handy here is Llama 3.2, and then we can do chat. Oh, what was wrong? Model. What happened? That was a lot of building up the excitement for the thing not to work. What did I do wrong? Model, that should be good. What? Oh, right, I see it, yeah. I should have done it full screen before. Yeah. Cool, now it finally works. So the thing loaded in 6 milliseconds. Let's see what it does and what it can know. It does show me some pretty warnings from JDK24, but if you say hello, it's up and running, and then we can ask it, what are you? And then it says, I'm Llama, and if you were to evaluate performance of this model, you can see that it's somewhere at 26 tokens per second, which is not the fastest in the world, but running on the machine where I have my editor, my slides, screen sharing, etc., I would say this is a decent performance. And if I run this on a Linux instance, it gets even better. And it's a proper LLM coming from Llama, so from Meta, so it has awareness of the real world. So I can even ask it, what do you know about Coimbra? And it will tell me that it's a charming city located in the center of Portugal with historical significance. What? Did it say something wrong? What happened? Tell me. What? What's so funny? I did not read the whole thing. Okay, supposedly it generates some output that might or might not be funny, but long story short, it is a fun educational project. And this is not necessarily to say that you need to replace your production deployment of OpenAI or Gemini or whatever with this model. But if you want something that runs locally with good performance and cheap or even for free because it runs on your machine, this is something that you can try for like test and development purposes. And also, we made sure to heavily document this code. So if you happen to be teaching students or something, this is something that you can use to educate students about modern Java and how to use the latest APIs to the fullest. Now, that was talking about how do you implement a complete inference engine in Java. And now let's talk about peak performance and how we can make applications with GraalVM go really fast. So hopefully by this point, we kind of noticed that GraalVM makes applications to run very fast. If you compare starting, let's say, your standard Spring web application on the JVM, which again on my machine can take 3 to 5 seconds, on native image it starts in maybe 100, 200 milliseconds. It also uses on average 3x, I would say, less memory. But what about peak throughput? Because depending on whom you ask, there could be different opinions about whether IoT or JIT compiled code can be faster or slower when it comes to peak throughput. And whenever I'm at a Java conference talking to Java developers, everyone says that they care the most about peak throughput. And again, depending on whom you ask, they will tell you that on the JVM, it is the only place where you can reach the best peak throughput, because as we know, JVM executes your code dynamically. As it runs, it looks at your code, it looks at what parts of the code are the most often executed, and where it makes sense to invest the compilation efforts, because it will invest those efforts into methods and loops that are most frequently executed. And native image, as we said at the beginning, it runs and builds your application ahead of time. So the runtime hasn't happened yet. So technically, there is no way of knowing which part of the application will be warm and where it makes sense to invest the compilation efforts. Let's take our application for a spin, and let's see how we can compare with JIT when it comes to peak throughput. So for that, we will go to yet another app. Let me just close this one and come back to my cloud setup. And let us go here, IoT performance. Now, here we will do a bit of performance benchmarking. And I need to say this disclaimer that clearly this will not be entirely scientific, because if I had to do scientific benchmarking, this would take me, I don't know, hours, if not the whole day, in a very configured, isolated environment. So this will be kind of quick napkin benchmarking, but for a conference talk, I think it will be enough. And again, for the sake of fairness, this is running on an isolated cloud instance, so hopefully there will be no inference with other processes. So let's take a look at our benchmark, and what will be benchmarking here will be a Spring Pad Cleaning application. Now, I will not run it because I hope you all by now know the Spring Pad Cleaning application, but that is, again, this kind of typical web enterprise app where you have your application, you have your database, and it emulates the work of an application that is at a pet clinic. So you can schedule visits for your pets there, you can read data about owners of the pets, read data, write data from the database, etc. So it emulates as much as possible a normal real-world application. And now let me talk about the benchmarking setup, because I'm quite proud of it. So first thing we will do, we will benchmark our application running on C2. And C2 is that standard JIT compiler in the OpenJDK. And on my machine, I only have GraalVM. That's the only distro I have. So to emulate C2, I will turn off GraalVM over here, So this will give me back my C2, the default JIT compiler in OpenJDK. So as I said before, we don't remove anything from the JDK. So if I want to have OpenJDK kind of set up on GraalVM, I'm just removing the Graal JIT and I have my C2. So we will turn off the GraalVM compiler, then we will start our Spring Pad cleaning jar. We will wait for 10 seconds for the application to start, because we notice that it starts in about 5 seconds, but just to be on the safe side, we will give it 10 seconds just to start. Then we will warm it up for 10 seconds. So we will start sending requests, but we are not measuring yet. We are giving the JVM a chance to warm up and see what's happening and optimize our application for peak throughput. And then for 20 seconds, we will actually benchmark and see how fast our application goes. So again, this is not entirely scientific, but almost as scientific as you can make it happen at a conference session. With that, let's start the script. Wait. Bench JIT C2. So now it will start, and as it starts, I also want to show you the actual request that we are sending, because we talked about the methodology, right? We sleep, we warm up, we benchmark, but what are the actual requests that we are sending? And requests are defined here. Wait, where are we? Yeah, those are requests. So instead of starting an application and just bombing the main page with, let's say, 1 million requests, what we are trying to do, we try to emulate a human behavior by going and creating an owner, then creating a path, then trying to read the data about owners and creating a visit. So instead, we access different endpoints and we combine both reading and writing data so that this will be a bit more fair instead of just overly optimizing for one specific endpoint. So this is a script, but it's trying to emulate kind of human behavior. As I was talking, my JIT setup on C2 has finished, and let's look at the numbers. So what I see in the first kind of warming up round, we have 559 requests per second, but this is to be expected. We know that the JVM warms up. In the beginning, it needs to do a bit of that housekeeping, but then it gets faster. And indeed, in this final benchmarking round, it did get faster. It got to 1.5 requests per second, so almost 3 times the throughput of this warming up round. So who thinks this is fast? Is it fast? Is it not? You're probably right about not giving an answer, because it's very hard to give those generic answers. It's better to see things in comparison, right? For that, let's run the same application on native image. And we will do the exact same setup where we are starting and waiting for 10 seconds and warming up and then doing the benchmarking run. And it will be funny because in the end, on the charts, we will see that this application didn't need to wait for 10 seconds because it doesn't need that much overhead housekeeping work to do as the JVM does. But we are doing it anyway, so we can have a kind of apples-to-apples comparison. So the benchmarking setup is absolutely the same. It's just that one application is the jar and the other application is a native application compiled with GraalVM. So it still runs the benchmark, but we can already see that the warming up run is twice as fast, even more, than the warming up run for the JVM. So it's, what is it, 1.2K as opposed to 500 requests for the JVM. But then in the end, when we have our final numbers, we see that the native application is at 1.1 and the JVM version is at 1.5. So it is somewhat slower. And here I could have said the disclaimer that, guys, benchmarking is complicated. It's not always, very accurate. And the JVM is an amazing piece of engineering. It's very hard to beat the JVM at peak throughput. But let's see if we can still beat it. So, not this way. Let's get it this way. For that, I will try yet another version of the application. So I have built an also native application, but with additional optimizations in place. And as this runs, let me super quickly show you the optimizations that we have used. Let me just maybe move this. OK, so what we have used here to make this application hopefully faster than the JVM, but let's see. So the number one step that you need to do if you want to have your native application run as fast or faster than the JVM is profile-guided optimizations or for short PGO. So what this does, it addresses that concern and that question that we get of how can we be as fast as the JVM if the JVM profiles application as it runs. So it collects metric and it sees where it makes sense to compile application. And we cannot do it because we built it ahead of time at build time and the runtime hasn't happened yet, right? So what you can do with PGO is you can build an instrumented version of your application. So you build an instrumented native image and then you hit it with a relevant workload. And it's very important to hit it with as relevant workload as possible. So you need to show your application what will need to happen at runtime, which parts of the application need to be executed and how often. And when you shut down that instrumented application, you get a profile files in your project folder, kind of similar to how the JVM does, but the JVM does it under the hood, so maybe you don't see it as obviously. And what it does, it collects information about the runtime behavior of your application that you can then use when you are building your app. And this way, we get that awareness of the runtime behavior of your application, kind of like the JVM does. And this way, we can combine the best of both worlds. So we are still compiling your application ahead of time. We have more time, we have more resources to optimize your app, but also we have those profiles that tell us how the app will perform at runtime. So we can combine those IoT optimizations with the runtime awareness that normally the JVM has. That helps, but that requires, as you might have noticed, two-step process where I'm building my instrumented application, I run it with the workload, and then I'm recompiling again with those profiles in place. And while it is very good for peak throughput, we understand that not everyone needs this absolutely best possible peak throughput. And you would think that in 2025, there could be a better way to solve this, maybe with AI and ML. And we saw the same thing. So now we ship in native image a little ML model that in case you don't give us profiles, it will look at your application and it will try to predict the profiles of your application. So it will try to predict which parts of your application will be warm, and based on those predictions, optimize your application. It will not be as accurate and as fast as your user-provided profiles, but it will give you maybe 8–10% performance improvement over not having profiles at all, which I think is really good. One more optimization, there are multiple GCs available for you in native image, but overall, if you want to have the best peak throughput, we recommend that you try out G1 GC. Typically, it will give you better peak throughput. And the last flag here is MARC native. This means optimize the application for the specific hardware features of this machine. So overall, native image builds applications that are specific to the operating system and architecture. So out of the box, I cannot build applications, let's say, on my MacBook for Linux, but still even MacBooks and even Apple Silicon Macs can have a variety of hardware features. So MARC native says, I'm not distributing these applications to other machines, just optimize for the best performance on this specific machine. So if you want to take a photo or if you want to make notes about how optimize peak throughput of native image, this will be the slide for that. And with that, let's go back to our benchmark and let's see how it did. Let me just zoom this out so it becomes a bit more readable. So our JVM finished at 1.5, let's say 1.58K requests per second. So this is the JVM number. Now, native image out of the box was at 1.18, and then native image with those optimizations in place, so PGO, G1 GC, and MARC native arrived at 1.6K requests per second. Now, there is indeed a bit of fluctuation, so those numbers vary a little bit depending on when I run it, there are multiple things at play. But overall, if you apply those optimizations that I have mentioned on the slide, you can have peak throughput on par with the JVM in addition to fast startup, low memory footprint, extra security, etc. with native image. So this was about peak throughput, but as our benchmark was running, we also did a bit of resources measurements, again, making a reference to Holly's session in the morning about how important it is not to use too many resources. It is nice if you can save some of that CPU and memory, because then you can use less hardware, you can pay less for your cloud, and you can also help the planet by not burning the resources you do not necessarily need. So as our application was running, we were also measuring how many resources each of those processes occupied. So let's take a look. This is our JET application running on C2. This is our native image application out of the box. And this is our final run, native with all the optimizations in place. And in case you're curious, in case you want to do this kind of benchmarking at home, the tool that produces those charts, it's called PS Record. It's a Python tool, so if you want to give it a try, that's the one to use. So what are we looking at here? The vertical red lines, that is CPU usage, and the horizontal blue line, that is memory usage. Now, what we see in the JVM run is that indeed it was starting, so just starting, but not even warming up for the first 5 seconds or so. Then there was a bit of this weird spike at 7 seconds, let's say, but overall it stabilized somewhere at like 10 seconds, and that's when our warming up run kicked in. So we see a lot of CPU as our requests come in, and JVM needs to optimize more and more. And then the CPU still is quite busy during the whole duration, but it stabilizes maybe after, like, I would say 30-ish seconds. And then the memory goes even a bit through the roof comparing to how the chart is set up. Maybe I need to give it more space for the memory usage. But all the runs run with the same memory requirement, so the JVM went even a bit overboard when we started hitting with an extra high load. Now, native image, remember how I told you in the beginning that it doesn't need 10 seconds to start, but we just want to have the same setup as we have with the JVM. And the same we see on those resources consumption charts, where the native image application starts, does a little bit work in the beginning, even less so here in the last one, and then it stabilizes and just waits for the request to come in. 2 more observations that I have here. So one is that native image uses less memory than the JVM. I think it's expected because we don't need to have the JVM around, we don't need to compile methods at runtime, etc. So overall, in both runs, it is lower than the JVM version, but it is a bit higher memory usage in the last setup because we are using the G1GC, and overall, I think it's a more or less known kind of notion that if you want to have more peak throughput, you need to give a bit more memory. So you can trade off memory for throughput, but still memory usage stays, I would say, reasonable. So hopefully this gets across the point that with native image you can have good peak throughput on par with the JVM, but also you can have less resources usage. So let me stop all of this and let's go to our final application. Before we do, just one more point regarding the energy savings. So again, with native image, you can reduce CPU and memory usage, but even if you care about things like electricity, maybe you work in an environment where there is, let's say, government requirement or regulatory requirement to have greener applications, to use less memory, and show what you are using to reduce your energy footprint. Here is a comparison of an application running on the JVM versus native image, where native image is the orange one on the right. And you can see that even with increased load, under constant load, it will still use less energy than running on the JVM. Now, let's talk about security, and this is a very fun topic. I like it a lot because when people talk about GraalVM and native image, they often mention fast startup, low memory usage, but it also offers an additional layer of security, and whenever I mention this to people, they get very excited because this seems to be lesser known. So where does it come from? First of all, native image, when it compiles your application, so when you run your native image command and you give it your application as a jar or as class files, it will look at your application starting from its main entry point, and then it will include everything that you need from your application, and that applies to your user code, the code that you yourself wrote, to the JDK libraries, etc. So it will analyze your project as a whole, and it will try to find everything that there is in your project, and then only include the things that you need that are actually involved in what your application is supposed to be doing into that native executable, and it will strip away everything that you don't need. So if there are some, let's say, JDK classes or dependency classes that you don't need, they will not be included in this native executable because we want to make it as slim as possible and strip away everything that you don't need. And this means that in a way we are reducing the attack surface because there are just fewer things in the application. So there is less to attack and less to kind of explore in your app. Also, things like reflection and serialization in native image, they are possible, but they require a specific allow list from your side. So you need to say, or your library and framework needs to say, please make this and that available at runtime in terms of reflection or serialization, and then only those things will be available. And this might be seen as a limitation in a way, but also it gives this additional security angle where you have more awareness and more control over what is happening and what is allowed in your application. So nothing can happen without you being in the know and without you granting that access. We also have support for SBOM, so you can explore and see what is inside your application in terms of dependency, and then you can use vulnerability scanners to actually scan your application. With that being said, let me show the application with SBOM support in action. And let me just remove this. OK. So for SBOM support, let's go here, native Spring Boot. And this will be a simple Spring application that I use all the time to test like the latest Spring capabilities and features, and also how they combine with GraalVM. And this is basically a simple Spring app that has a couple of controllers, and it has a couple of standard Spring dependencies, such as Spring Web, Spring Data, etc. So let's see what we have compiled here already. And I have this application called Demo SBOM. So as you can see from the name, it includes an SBOM, so software bill of material, to have a way to see what is inside my application in terms of the dependencies. So let's see what we can do with that. Let me just move this up. So the way to retrieve this will be, there are multiple ways to work with SBOM, but the one that I like would be to use native image inspect. And then we pass the SBOM flag. And then we need to pass the actual native executable, so demo SBOM. And then this is something we can feed directly into a vulnerability scanner, whatever you like. I like Gripe. And this will analyze my application using Gripe, and it was able to see what's inside the app, and it detected that there are 38 packages in my app, but there are no vulnerabilities found in that application, so we are all good, all set. Yet another way to work with this would be is that I can run my app, so demo SBOM, and then this was built with SBOM, but also with Spring Actuator. So if I go to Actuator, Spring knows where that SBOM file is in my application, and here I can retrieve it, and maybe this is something I want to have running in production internally at my company. So when my security team comes to me and says, we need to scan your applications and see what you are running and what's inside those applications, you can just point them to endpoint, and they will be able to scan it. And one more thing that I like here, this was added in the last release of GraalVM. We have added this information of depends on, so I can see how my dependencies in this SBOM depend on one another. So let's say if I have my, if I have my Spring Web, that in turn brings in my Spring Beans, Spring Core, etc. So this is something I can explore in my SBOM. And then in the last release of GraalVM, we have also added a capability where we can include literally everything that we know about your application in this SBOM. So every single field, method, etc. that we have included, if you want, you can build a super detailed, super long, super heavy SBOM that details all the information that we know about your application. So this looks nice. And I mean, what we ran before was the inspect. This, I would say, is something that I would like to see in my production where things run, but they are not vulnerable, so we are all safe. But I would say this makes for a slightly less exciting conference demo. So let's see if we can make it a bit more exciting. For that, let me go to a place with an intriguing name, Native Spring Boot Vulnerable. And this will be a very similar application, only there I brought in a very old version of JSON. Where is it? Are we looking in the right place? Yes. JSON. So yeah, a very old version, and then I brought it in as a dependency, but also I made sure my application actually uses it, because if I just add it to my POM.xml but I don't use it, native image will strip it away. But here we actually used it. So let's scan this application now. So when we scan this application with that very old version of JSON, where are we? Demo SBOM. Yeah, we're in the right place. Inspect. let's try like this. Okay, something has happened and I don't have time to figure it out, but this would have complained to me that my application is vulnerable because there is that vulnerable version of JSON. So let's imagine here we had a vulnerability warning saying that we are using a vulnerable version of dependency. And I see that I only have 2 minutes left, so let me see if I can wrap up. 2 minutes. Do we want to see links and wrap up, or do we want to see a demo of Python embedded in Java? Python? Okay, half of the room. I can do it super quickly, hopefully. Let's see. Let's go high up, and let's go GraalVM, and let's start it, target demo. So this application is, again, a Spring application that uses Python to produce a very beautiful chart that we'll hopefully see in the second. And if we go here, localhost Python. So this chart that is also interacting, it is coming from PyGal library in Python. And the way to bring this in is just you add our GraalVM as a dependency, and you can start programming and using Python libraries directly in your Java applications, and you can even compile them as native images. So that was maybe the fastest demo in the history of me publicly speaking. To wrap it up, because I have 1 minute, if you want to get started with GraalVM, those are all the links. So you can start with the docs and samples. And if you are using SDK-man, which you should, I think it's the best way to manage SDK installations, you can just get GraalVM from SDK-man. And if you want to get all the links, slides, etc., you can just go to this GitHub repo, and this is what I use for this talk with all the links. With that, I have stickers, and if you want to come talk to me and have questions, please just come here under the stage. Thank you so much.